Hello, you're welcome back. All right, so we'll continue with transistors, and of course, we're going to be looking at the configuration, different transistor circuit configuration. Okay, now we already know that the transistor have three terminals, which of course include the emitter, base, and the collector. Okay, and we already said that the emitter base is always forward biased, while the collector base is always reverse biased. Okay, so now we're going to be looking at different configuration of a transistor. Okay, different circuits, and that configuration is based on how the input is being connected, okay, with respect to the output. Remember, there are three terminals. Okay, two terminals will be for the input, where two terminals will be for the output. Since there are three terminals, that means one terminal will always be common. Okay, for example, if I want to apply my input, okay, between base, okay, between emitter and base, all right, that means invariably I can also choose to decide to take out my output, okay, between collector and also base. So you discover that one particular terminal is common, which is the base. All right. So I can actually go the other way around, making one terminal to be common. Okay. I can go the other way around. Let me show you what I would do. Okay. Apart from this, I can go the other way around. Let me rotate this vertically. Okay. Okay, so I can still go this other way around, okay? Making a meter common, all right? Connecting my input between the emitter and the base, and the output is connected between the collector and of course the emitter. So as you can see here in this connection that the emitter is common. So a transistor can have different configuration depending on the kind of result you want to get out of this transistor. So we are going to be looking at different circuit configuration of a transistor, and of course the parameters, okay, that we need to evaluate for each configuration. All right, so now let's start with, we have three configuration. Okay, so number one configuration, we have common base. Okay, common base configuration, common base. So that common base configuration, we'll call it CB. Okay, that's abbreviated as CB. Number two, we have common emitter configuration. So common emitter, that means emitter is actually common for the two output. Common emitter configuration. Okay, and that's abbreviated as CE. Then number three, we have uh, common common collector configuration. Common collector, okay, configuration, and that is CC. Okay, so now let's actually start with the very first, which is common common base configuration. Okay, common base. So I will draw the circuit diagram. Okay, for a common base configuration, of course, I have I'm gonna okay draw the circuits this way. All right, and of course I'll take out my terminals. Now this is the base. Okay, of course this is the base. This is the emitter. Okay, this is I'm using NPN transistor. Of course, you should know that. And this is the collector. So the base is common. So I'm gonna bias. Okay, connect a bias voltage. Remember, emitter base is always for bias. All right. So since I'm dealing with NPN, no, if it's NPN, this is N, this is P, and this is N. Okay. So the N are connected to the N, of course, the P. So that is the appropriate bias. So the current actually flows. Okay. Now, I also take this out. Okay. Then of course, no, this is actually reverse biased. Reverse bias, the negative connected to the positive, and of course, the positive, okay, connected to the negative. All right. So this is a common base configuration of transistor. Now, there's something you should know about the current of transistor. Remember, a transistor, have we talked about this? It has the emitter current, which is IE, has the base current, which is IB, and it has the correct collector current, which is IC. Okay. Now, there's something you should know. The emitter current, okay, according to Kirchhoff law, is always equal to the base current plus the collector current. Okay, I can actually prove that. Let's prove that with the configuration we have before. Okay, let's say we have this transistor. Okay, having terminal N P N. All right, I take out the three terminals. Okay, so you know very well, as we already said. Okay, of course, for NPN, no current always move from P to N. Okay, so this is my NPN. Okay, this is my emitter, right? This is my base, and this is my collector. So current always flow this way. This is current. So current is flowing from the base to the emitter, and of course, this happen also flows from the uh, base again to the collector. All right. So you discover that this is IE. IE is flowing out. Okay. Then IE is flowing out. Then you discover that this is actually a node. Okay. This is a node. Please pardon me. I made a mistake. Collector base is always reverse bias. Okay. So the current will be flowing in. So base also flows in, but collector, okay, the collector current flows in. IC flows in into this junction. Okay, the base current also flow into the junction, right? But the emitter actually flows out of the junction. All right. So now, in a nutshell, okay, let me not go into that. Always know that for any configuration of transistor, the emitter current is always equal to base current plus collector current. Okay. So emitter current is equal to the base current plus collector current. That's the very first thing you should actually take note of. Okay, so now let's now look at what happens when we actually uh, establish this connection. Okay, when we establish this connection, you know very well that the base is common, right? So the input, our input, is actually connected between the emitter and the base, while the output, okay, is taken between the collector and the base, okay, which gives me an output. So my output, the output current here is the collector current. This collector current is the output current, okay, while the base current, i.e., is my input current, okay, the base current is my input current. So that means in this particular configuration, my input was E, all right, IE. So it was transferred, it was translated to IC as an output. So the very first parameter we actually need to write down, okay, or state is what is known as the DC transfer ratio, direct current transfer ratio. Of course, direct current transfer ratio um, of a common base configuration, we use the symbol alpha to represent it. What is transfer ratio? The direct current transfer ratio is the ratio of the output current to the ratio of the input current. The output current in a common base is collector current, while the input current is the emitter current. Okay, so the ratio, the transfer ratio is going to be equal to the output collector current, and of course divided by the input, which of course is the emitter current. Okay, so please take note of this. For a common base configuration, DC transfer ratio of a common base configuration is given as IC all over IE. So if I cross multiply this particular ratio now, I can simply say that my output, which is collector current, okay, if I cross multiply, is going to be equal to alpha multiplied by IE. So please take note of this. So if I want to get, anytime I want to get my collector current, my output current, all I just need to multiply, I multiply the ratio, the transfer ratio by the base current, okay? Please take note of that. So I'll call this, let me call this one equation 1. I call this equation 2, perhaps. I call this equation 3. I'm going to generate an equation. So now knowing that IC is equal to alpha IE, okay? So I'm going to look at the relationship. So I'm going to substitute that into equation 1. So substitute substitute the collector current IC being equal to alpha IE, okay, into equation 1, okay? Equation 1. So from my equation 1, I have okay, IE is gonna be equal to IB. All right. Then of course it's gonna plus IC. Already IC is equal to alpha IE. Okay. So this is one relationship. So IE is always equal to IB plus alpha IE. All right. Now I can rearrange this equation now. I can rearrange this equation by making, I want to make IB the subject of the formula. So the base current IB, if I rearrange the equation, I take this to the other side, that's gonna give me emitter current, then of course minus alpha IE, alpha emitter current. Okay, so the base current IB is going to be equal to, I have to factorize, okay? IE is actually a common factor, take it out. All right, then open bracket. This is going to be 1 minus alpha IE. 1 minus alpha, please pardon me, IE is already a common factor. All right, so base current is always equal to emitter current, then multiplied by 1 minus alpha. So I hope that is well understood. So please, this formula is very important. So I call this formula. In fact, the formula number 4 is important because we are gonna revisit formula number 4 again. Okay. So this is how a transistor is being connected in a common base configuration. So I hope that is well understood. Okay, so let's look at the next configuration. The next configuration is common emitter configuration. Common emitter. Okay. All right. Now, in the common emitter configuration, of course, you know exactly how that is gonna work. Okay, emitter. Please pardon me. Emitter is just one M. Okay. It's just one M, then double T. Emitter. So, of course, we abbreviate that as CE. So anytime you see there's a CCE as an abbreviation, is common emitter configuration of transistor. Okay, let's do that. Let's do that. So in this case now, I'm going to write the circle symbol of a transistor in a common emitter mode. Okay. All right. So of course you know that this is I'm still using NPN. NPN. All right. So the emitter is common. I can even ground it. Okay, connect it to a ground, a common ground. So I'll take out. All right. So if I'm using NPN, of course, this is gonna be of course this is gonna be N, okay, this P and this N, right? Okay, please pardon me, let me put it this way. I'm using NPN, right? So the base is and the emitter here is P and this N, all right? So of course, you know, collector. Okay, let's not just talk about that. Uh let's connect our circuit, okay? So this is where I'm taking my output. Of course, my input is gonna be across this. Okay, this is the base. Of course, this is the emitter. and this is the collector. Okay, the base, the emitter, and the collector. All right, so of course the base emitter is always, you know very well that they are always uh, forward bias. Okay, so negative will be connected to negative, positives connected to positive, right? You know that already. Okay, so for this also, let me connect it in a forward bias. All right, so now let's proceed. Of course, you know, in the case ours, don't forget the fact that my emitter current, okay, for any of the configuration is still equal to the base current plus the collector current. Don't forget this relationship, okay? This relationship is constant. All right, so of course, this is here lies my base current. So the base current now came out. My base current is the input. Don't forget. The base current here is the input. That's where I'm taking my input. While the collector current, IC, is now going to be my output. All right, output. So we're going to look at another the DC transfer ratio. Okay, so DC, direct current transfer ratio of a common emitter configuration, okay, of a transistor. This time around, the symbol that is used for is beta, not alpha. Okay, the symbol is, so of course the ratio is always output all over input. The output is still IC, and this time around the input is IB. All right, IC all over IB. So now you know what happens. So if I want to get my output current IC across multiplier, is going to be equal to beta multiplied by IB. Okay, so it is going to be beta multiplied by IB. So please take note of that. So now with what I have here now, you know what I'm going to do. Okay, so I'm going to actually establish a relationship. Of course, let me still call this equation, what will I call it? Okay, can just give it any, let me call it one, any number you want to give it. Okay, call this 3. Okay, so from what we have here, IC is equal to beta IB. So invariably now I can simply say that IE from this relationship from 1, okay, from equation 1. If I substitute IC being equal to beta IB, so this I'm going to have IE is going to be equal to IB, then plus IC, which is beta IB. Okay, so how does that actually help me? Let's flow with it. You know very well that IB, so IE now is going to be equal to, you know very well that IB here is a common factor, so I take it out. Then I open a bracket. This is going to be equal to 1 plus beta. Okay, so this is another relationship. So for IE is equal to 1 plus beta. Okay, IE is equal to I is equal to IB, then multiply by IB multiplied by 1 plus beta. Okay, so please take this note of this formula. Okay, so don't, I'm going to actually reiterate the two formula we had before. Okay, remember previously we have said that IB, okay, is equal to IE, all right, multiplied by 1 minus alpha. Don't forget this formula. Now we are saying that IE is equal to IB multiplied by 1 plus beta. Okay, so we are going to actually combine these two relationships. All right, So in the next video, we're going to be looking at the relationship between alpha, okay, the DC transfer ratio of common base, and beta, which is of course the DC transfer ratio of a common emitter. Okay, so we're going to combine all this formula to generate a relationship. All right, so see you in the next video. Thank you very much.